Hello, and welcome to our astronomy course. Today, uh, we are going to study modern cosmology. And the first subtopic today's lecture will be a wide space, time, matter, and the cosmology of general. Okay? So, how can the Big Bang have happened everywhere? How do you think? To solve the puzzle, you must put similarly reasonable expectations aside and look carefully at how space and time behave on cosmic scale. The universe looked about the same in whichever direction you observe. The property of being the same in all directions is called isotropy. Of course, there are local differences. Yeah, if you look toward a galaxy cluster, you see more galaxies, but that is only a local variation. On the average, you see similar numbers of galaxies in every direction. Furthermore, the background radiation is almost perfectly uniform across the total sky. The universe is observed to be highly isotropic. The universe also seems about the same everywhere. The property of being the same in all places and is called homogeneity. Of course, there are local variations. Some regions contain more galaxies and some less. Also, because the universe evolved, then the large look-back times you see galaxies at an earlier developmental stage. But if you account for these well-understood variations, then the universe seems to be on average the same everywhere. Isotropy and homogeneity lead to the cosmological principle, which says that any observer in any galaxy sees the same general properties for the universe. As you just learned, this overall principle intentionally overlooks minor local and evolutionary variations. The cosmological principle implies there are no special places in the universe. Are you understand me? Okay. What you see from the Milky Way galaxy is typical of what all intelligent creatures see from their respective galaxies. Furthermore, the cosmological principle states in a new form the idea that the universe can have no center or edge. Such locations would be special places, and the cosmological principle says there are no special places. Einstein's theory of general relativity, published, by the way, in 1916, describes space and time together as a fabric of the universe, called space-time. That idea will give you a new insight into the meaning of the phrase expanding the universe. General relativity describes space-time as if it is made of stretching rubber. And that explains one of the most important observations in cosmology, the red shift. It is a common misconception that cosmological redshifts are Doppler shifts of galaxies flying away through the space. Instead, except for small local motion within cluster of galaxies, the galaxies are at rest. They are being separated from each other as space-time expands. Also, as space-time expands, it stretches any photon traveling through space, and so that its wavelength increases. Photons from distant galaxies spend more time traveling through space and are stretched more. In other words, have larger redshift than photons from nearby galaxies. That is why redshift depends on distance, as you can see from this slide. Okay? Astronomers often express redshift as if they were actual radial velocity, but the redshift of the galaxy are not Doppler shifts. That is why my lecture is careful to refer to a galaxy's apparent velocity of recession. Some textbooks convert cosmological redshift to velocities using Einstein's relativistic Doppler formula. But that formula applies to motion through space and not to the behavior of space-time itself. So that formula should not be used in a cosmological context. The Hubble law still applies. Redshift can be used to find the distance to galaxies, because redshifts show how much the universe has expanded, and thus how much time has elapsed since the photons started on their journey. Almost immediately after Einstein published his general relativity theory, other theories were able to solve the sophisticated mathematics and compute simplified descriptions of the behavior of space, time, and matter. The resulting model universes dominated cosmology throughout the 20th century. The equations allowed three possibilities. Space-time might be carved in either of two different ways, or it might have no curvature at all. Most people find this carved model difficult to imagine. And modern observations have shown that the simplest model without curvature is almost certainly correct. So you don't have to wrap your brain around the carved models. You might, however, like to know a few of their most important properties. Some models predicted that space-time is carved back on itself to form a closed universe. You would not notice this curvature in daily life. It would only be evident in measurement involving very distant objects. Throughout the 20th century, observations could not eliminate closed models, so they were considered a real possibility. Closed universe models have finite volume, but because space-time is carved back on itself, a closed universe nevertheless would have no edge and no center. Such closed models predicted that the expansion of the universe would eventually become a contraction that would bring all of the matter and energy back to the high-density Big Bang state, which was sometimes called the Big Crunch. Other models predicted an uncarved or flat universe. That is the kind of space-time you would expect from your daily life, with the same rules of geometry, even for cosmological distances that you learn in high school. Flat models are infinite, have no edge or center, and expand forever. A third kind of model predicted an open universe. Such models contain carved space-time, but are not carved back on themselves. Like the flat models, open models are infinite, have no center or edge, and expand forever. Cosmologists of the 20th century struggled to find the reasons of or observations that would allow them to choose among these three kinds of models. The main clue was density. According to general relativity, the overall curvature of space-time is determined by the average density of matter plus energy in the universe. Cosmologists could calculate that space-time is flat if the average density of the universe equals a critical density of 9 times 10 in power minus 27 kilogram per cubic meter. If the average density of the universe is more than the critical density, the universe must be closed. And if it is less, the universe must be open. Attempts to measure the density, however, were inconclusive. These three kinds of universe models are illustrated in this figure, which compare the expansions versus time on the different models. The parameter r, scale in universe parameter r, on the vertical axis is a measure of extent to which the universe has expanded. You can think of r in a highly simplified way as the average distance between galaxies. In the figure, you can see that closed universes expand and then contract while closed universe in the blue, yes, less than the flat sheet closed, and that contrast while the flat and open universe expanded forever. Notice that you can't find the actual edge of universe unless you know whether it is open, closed, or flat. The Hubble time is the edge the universe would have if it were totally open, which means it would have to contain almost no matter at all. If the universe contains enough matter to make it flat, then its age would be 203 of the Hubble time. If age for Hubble is about 70 kilometers per second for the megaparsec, as astronomers have measured, and the universe is flat, then it should be only 9.5 billion years old. But you remember the actual age of our universe. Astronomers know of global star clusters that are older than that. So this was known as the age problem. How can the universe be younger than the sum of the objects in it? Modern observations show that the universe is flat, and later in this lecture, you will see how the evidence eliminated carved models and solved the age problem. For now, however, you can think about a different path. If the universe is flat, then its average density must equal the critical density. Yet, when cosmologists added up the matter that could be detected, they found only a few percent of the critical density. They wondered if the dark matter made up the rest. There is more to the universe than meets the eye. A couple lectures ago, you discovered that galaxies have much stronger gravitational fields than you would predict based on the amount of visible matter. Their gravitational fields are much stronger than expected, even when you add in the in the gravity of the gas and dust that would be contained in the galaxy. Galaxies must contain dark matter. This is not a small issue. Look at this figure. Gravitational lengthening is dramatic evidence of dark matter. The galaxy cluster in the figure contains so much dark matter that it wraps space-time and focuses the images of more distant galaxies into short arcs of light. The universe contains much more dark matter than normal matter. Looking at the universe of visible matter in galaxies is like looking at a tree and seeing only the leaves. Modern evidence shows that the dark matter is not the same as the normal matter you are made of. To follow that argument, you need to estimate the density of normal matter. And you can start with what is known about conditions right after the Big Bang. As you have learned, during the first few minutes of the Big Bang, nuclear reactions converted some protons into helium and very small amount into the other elements. How much of elements heavier than helium was produced depended on the density of normal matter during the Big Bang. For example, if the density of matter were high, so that there were lots of normal particles such as protons and neutrons flying around, they would have collided with the deuterium nuclei and converted most of them into helium, right? On the other hand, if the density of normal particles had been relatively low, more deuterium would have survived intact without being converted to helium. Lithium is another nucleus that could have been made in small amounts during the Big Bang. And this figure shows that there is a gap between helium, look at this moment, between helium-4 and lithium-6. So between gap between helium and lithium. There is no stable nucleus with atomic mass 5. So regular nuclear reaction during the first few minutes of the Big Bang had difficulty converting helium into lithium. If, however, the density of proton and neutron was high enough, a few nuclear reactions could have left the gap and produces a small amount of isotope lithium-7. Both deuterium and lithium are destroyed in stars. So astronomers attempt the difficult task of studying clouds of gas at large look-back times that had not yet been altered by nuclear reaction in stars. As shown in this figure, the amount of deuterium absorbed now in the universe sets a lower limit of the density of the universe relative to the critical density, and the observed abundance of lithium-7 sets an upper limit. So, the surprising conclusion from this observation and calculation is that normal matter from which you, Earth, and the stars are made cannot make up much more than 4% of the critical density. Yet, observation of gravitational effects show that galaxies and galaxy clusters contain much larger amounts of matter than that, which can't be normal matter, but instead must be dark matter. The protons and neutrons that make up normal matter belong to a family of subatomic particles called baryons. So cosmologists think that most of the dark matter cannot be baryon. Only a small amount of the mass in the universe can be baryonic. The dark matter must be non-baryonic matter. Some theorists thought that neutrinos, particles which are predicted to be very abundant in the universe, yet are not baryon, might have enough mass to make up the dark matter. But modern measurements show that neutrinos are not massive enough. Some particle physics theories predict the existence of WIMPs, weakly interacting massive particles, WIMP, weakly interacting massive particles. But they have not been detected with certainty in the laboratory. The true nature of dark matter remains one of the mysteries of the astronomy. Theoretical models of galaxy formation in the early universe provide more hints about the nature of dark matter. If dark matter is composed of particles that were moving at or near the speed of light, when matter and energy had equal density, it is called hot dark matter. Such fast-moving particles do not clump together easily and could not have stimulated the formation of objects as small as galaxies and clusters of the galaxies. Instead, the most successful models of galaxy formation require that the dark matter be made up of cold dark matter, meaning the particles move slowly and could clump into relatively small structures. Non-baryonic dark matter does not interact significantly with normal matter or with photons, which is why you can't see it. This also means that dark matter was not affected by the intense radiation that dominated the universe when it was very young. So long as radiation dominated the universe, it prevented normal matter from contracting to begin forming galaxies. But the dark matter was immune to the radiation, and the dark matter could contract to form clumps while the universe was very young. In other words, dark matter could have given galaxy formation a head start soon after the Big Bang. Models with cold, non-baryonic dark matter are almost successful at predicting the formation of galaxies and clusters of galaxies with the right size and the right time in the history of the universe to match their observation. Also, the evidence is very strong that plenty of dark matter exists. It is still not abundant enough to make the universe flat. Dark matter appears to constitute less than 30% of the critical density. As we will see a bit later in this module, there is no more to the universe than meets the eye, more even than dark matter. Now, let's analyze scientific argument. Why do cosmologists think that dark matter can't be baryonic? Good scientific arguments always fall back on evidence. In this case, The evidence is very compelling. Small amounts of isotopes like deuterium and lithium-7 were produced in the first minutes of the Big Bang, and the resulting abundance of those elements depends strongly on how many protons and neutrons were available at that time. Because those particles belong to the family of the particles called baryons. And physicists refer to the normal matter as baryonic. Measurements of the abundances of deuterium and lithium have that the universe cannot contain more baryons than about 4% of the critical density. And observations of galaxies and galaxy clusters show that dark matter must make up almost 30% of the critical density. Consequently, cosmologists conclude that the dark matter must be made up of non-baryonic particles. Finding the dark matter is important because the density of matter in the universe determines the curvature of space-time. Now, build a new argument. How does the modern understanding of space-time explain cosmic redshift? How do you think? And let's study next topic, 21st century cosmology. If you are a little dizzy from the weirdness of expanding space-time and dark matter, make sure you are sitting down before you read and listening further. As the 21st century began, astronomers made a discovery that started all cosmologies. The expansion of the universe is accelerating. You have to go back to a couple of decades to understand how that amazing new discovery nevertheless fits well with some of the things you have been learning in this lecture. By 1980, accumulating evidence had made the Big Bang theory widely accepted by cosmology. But it faced two problems that led to the development of a new theory, a revised Big Bang, with an important addition. One of the problems is called the flatness problem. The properties of the universe appear to be close to the dividing line between being open or closed. That is, the geometry of the universe seems nearly flat. Given the vast range of possibilities, from zero to infinity, it seems peculiar that the density of the universe is close to the critical density that would make it exactly flat. If dark matter is as common as the measurements indicate, the universe density must be within a factor of 3 of the critical density. You saw as a factor more 3, it is this one. Even a small departure from the critical density when the universe was young would be magnified by subsequent expansion. To be so near critical density now, the density of the universe during its first moments must have been within 1 part in 1049 of the critical density. So, the flatness problem can be started as: why is the universe so close to perfectly flat? The second problem with the original Big Bang theory is called the horizon problem. This is related to the observed isotropy of the cosmic microwave background radiation. When astronomers make a correction for the motion of Earth, they see the same intensity and temperature of the ground radiation in all directions to a precision of better than 1 part in 1,000. Yet, when you observe the ground radiation coming from 2 points in the sky, separated by an angle larger than about 1 degree, very, very small, you are looking at 2 bits of matter that seemingly should never have been connected from the Big Bang up to the time when the radiation was emitted. That is, when recombination occurred and the gas of the Big Bang became transparent to the background radiation, the universe was not old enough for any form of energy to have traveled from one of those 2 regions to the other. And thus, according to the standard Big Bang theory, the 2 spots you observe had not had enough time since the start of the Big Bang to exchange energy and even out their temperatures. And then, how did every part of the entire Big Bang universe get to be so nearly the same temperature at the time of recombination? This term horizon is used because the 2 spots are said to lie beyond their respective light travel horizons. The key to these 2 problems and to others involving subatomic physics may lie with a theory called the inflationary universe, because it predicts a sudden rapid expansion called inflation, when the universe was very young, a violent expansion even more extreme than that predicted by the original Big Bang theory. To understand the inflationary universe, you need to recall that physics is known of only 4 forces: gravity, the electromagnetic force, and the strong force, and the big force. Only 4, right? And you are familiar with gravity. You fought it to get out of bed this morning. The electromagnetic force is responsible for making magnets stick to refrigerated doors and cat hair stick to sweeter charged with static electricity. Okay? As well as holding electrons in orbit around atomic nuclei and being intimately connected with processes that make light and radiation. The strong force holds atomic nuclei together, and the big force is involved in certain kinds of radioactive decay. For many years, theorists have tried to unify these forces. That is, they have tried to describe all 4 forces as aspects of a single mathematical law. A century ago, James Clerk Maxwell showed that the electric force and the magnetic force were really the same effect, and the physicists now count them as a single electromagnetic force. Similarly, in the 1960s, theorists succeeded in unifying the electromagnetic force and the weak force in what is now called the electroweak force. But those 2 forces operate effectively as a single unified force only in a very high energy processing. At lower energy, the electromagnetic force and the weak force behave differently. Now, theorists have proposed ways of unifying the electroweak force with the strong force at even higher energy. These new theories are called ground unified theories, or GUP, ground unified theories. According to the inflationary universe, the universe expanded and cooled until about 10 in power minus 35 seconds after the Big Bang, when it became cool enough that the electroweak force and the strong force began to disconnect from each other. That is, they began to behave in different ways, as you can see from this picture. This change released tremendous energy, which suddenly inflated the universe by a size factor between 1020 and 1030. At the start of inflation, the part of the universe that is now observable from Earth is calculated to have been no larger than the volume of an atom. But it suddenly inflated to the volume of a cherry pit and then continued its slower expansion to its present extent. Early rapid inflation of the universe can solve both the flatness problem and the horizon problem. The sudden inflation of the universe would have forced whatever curvature it had before, that moment towards the value of zero, just as inflating a balloon makes a small spot on its surface flatter. But secondly, you now live in a universe that is almost perfectly flat because of that long ago moment of inflation. In addition, because the entire observable part of the universe was once no larger in volume than an atom, it would have had enough time to equalize its temperature before inflation occurred. As a result, you now live in a universe in which the background radiation has the same temperature in all directions. The inflationary theory predicts that the universe is almost perfectly flat, which means that the actual density equals the critical density. A theory can never be used as evidence, of course, but the beauty and simplicity of the inflationary theory has given many cosmologists confidence that the universe must be flat. Observations, however, seem to say that the universe does not contain enough matter, ordinary baryonic matter plus non-baryonic dark matter, to be flat. Can there be more to the universe than baryonic matter and dark matter? What do you think? And what could be weirder and more obscure than dark matter? Let's go on. Both common sense and the theory of general relativity suggest that as the galaxies recede from each other, the expansion should be slowed by gravity trying to pull the galaxies toward each other. How much the expansion is slow should depend on the atom of matter in the universe. If the density of matter and energy in the universe is less than the critical density, the expansion should be slowed only somewhat, and the universe should expand forever. But if the density of matter and energy is greater than the critical density, the expansion should be slowing down dramatically, and the universe should eventually begin contracting. Notice that this is the same as saying a low density universe should be open, and a high enough density universe should be closed. For decades, several times teams of astronomers struggled to measure the redshifts and distances to very distant galaxies and detect the slowing of the expansion. Detecting a change in the rate of expansion is difficult because it requires accurate measurements of the distances to very remote galaxies. The COMP research teams use the same technique of calibrating type 1a supernova as distance indicator. As you learned in the middle of this semester, I hope you remember this, okay? A type of 1a supernova occurs when a white dwarf gains matter from a companion star, exceeds the Chandrasekhar limit. Do you remember this term, Chandrasekhar limit? And collapses in a supernova explosion. Because all such white dwarfs should collapse at the same mass threshold, they should all produce explosions of the same size and luminosity, which makes them good distance indicator. The two teams calibrated type 1a supernova by locating such supernova occurring in nearby galaxies, with distances known from Cepheid variables and other reliable distance indicators. Once the peak luminosity of type 1a supernova had been determined, they could be used to find the distances of much more distant galaxies. Both teams announced their results in 1998. They agreed that the expansion of the universe is not slowing down. Contrary to expectation, it is speeding up. That is, the expansion of the universe is accelerating, as you look from this picture. The announcement that the expectation of the universe is accelerating was totally unexpected, and astronomers immediately began testing it. This conclusion depends critically on the calibration of type 1a supernova as distance indicator. And some astronomers suggested that the calibration might be wrong. Problems with the calibration have been ruled out by subsequently observed supernova at even greater distance. The universe really does seem to be expanding faster and faster, rather than slowing down. If the expansion of the universe is accelerating, then there must be a force of repulsion in the universe that counteracts gravity, and cosmologists are struggling to understand what it could be. One possibility leads back to the 1916, when Albert Einstein published his theory of general relativity in that year, namely in 1916. And he recognized that his equation describing space-time implied that the galaxies could not float unmoving in space, because their gravity would pull them toward each other. The only solution seemed to be either a universe that was contracting under the influence of gravity, or a universe in which the galaxies were rushing away from each other so rapidly that gravity could not pull them together. In 1916, cosmologists did not yet know that the universe was expanding. So Einstein made what he later thought was a mistake. The balance, the attractive force of gravity. Einstein added a constant to his equation called the cosmological constant, represented by an uppercase lambda, lambda from T. That constant represents a force of repulsion that balances the gravitational attraction between galaxies so the universe would not contract or expand. 13 years later, in 1929, Edwin Hubble announced his observations indicating that the universe is expanding, and Einstein said introducing the cosmological constant was his biggest blunder. Modern cosmologists think he may have been right after all. One explanation for the acceleration of the universe is that the cosmological constant represents a force that causes a continuing acceleration in the expansion of the universe. Because the cosmological constant, by definition, remains constant with time, and the universe would have experienced this acceleration throughout its history. Another solution is to suppose that totally empty space, the vacuum, contains energy, which drives the acceleration. This is an interesting possibility because for years theoretical physicists have discussed the idea that empty space contains energy. Cosmologists have begun referring to this energy of the vacuum as quintessence. So, unlike the cosmological constant, quintessence would not necessarily remain constant over time. Whatever the correct explanation might be, the observed acceleration of the universe expansion is evidence that some form of energy is spread throughout space. Cosmologists refer to it as dark energy, an energy that drives the acceleration of the universe, but does not contribute to the formation of starlight or the cosmic microwave background radiation. You will recall that acceleration and dark energy were first discovered when astronomers found that supernovae a few billion light years away were slightly fainter than expected based on their redshift. The acceleration of the expansion has made those supernovae a bit farther away than implied by their redshift, and so they look fainter. Since then, astronomers have continued to find even more distant type 1a supernovae, some as distant as 12 billion light years. The more distant of those supernovae are not too faint, they are too bright. That reveals even more about dark energy. Unlike the medium distant supernova, the very distant supernova are a bit too bright because they are not as far away as expected. And that confirms a theoretical prediction based on dark energy. When the universe was young, galaxies were closer together, and their gravitational pull on each other was stronger than the effect of dark energy and slowed the expansion. That makes the very distant supernova a bit too bright. As space-time expanded, it moved the galaxies farther apart, and their gravitational pull on each other became weaker than dark energy, and acceleration began. That makes the medium distance supernova a bit too faint. In other words, the observations show that sometime about 6 billion years, this is equal to 40% of the age of the universe ago, the universe shifted gears from deceleration to acceleration. The calibration of type 1a supernova allows astronomers to observe this change from deceleration to acceleration. Furthermore, dark energy can help you understand the curvature of the universe. The theory of inflation makes the specific prediction that the universe is flat. Recent observations you will learn about in the rest of this module confirm that prediction. Dark energy seems to explain how the universe can have enough matter plus energy to be flat. As you have already learned, you remember the classical formula: energy equals mc squared, means that energy and matter are equivalent. And thus, the dark energy is equivalent to an amount of mass spread through space, right? Baryonic matter plus dark matter makes up about 1/3 of the critical density. And dark energy appears to make up the remaining 2/3. That is, when you include dark energy, the total density of the universe equals the critical density, which makes the universe flat. Step by step, you have been climbing the cosmological pyramid. Each step has been small and logical, but looks where it has led you. You now know some of the nature's deepest secrets, but there are yet more steps above and more secrets to explore. Accelerations helps with another problem. The Hubble constant equals 70 kilometers per second per megaparsec. And earlier in this lecture, you calculated the Hubble time, an estimate of the age of the universe, and found it was about 14 billion years, right? Further, you calculated a more precise estimate of the universe age on the assumption that its geometry is flat, which gives an age of 2/3 of the Hubble time, of 2/3 times 14 billion years, which equals about 9 billion years, right? That was a puzzle because the globular star clusters are older than that. Now you are ready to solve the age problem and then consider the fate of the universe. If the expansion of the universe has been accelerated, then it must have been expanding slower in the past. And the galaxies would have taken longer to arrive at the average separation you can observe now. That means the universe can be flat, but nevertheless older than 2/3 of the Hubble time. The latest estimates suggest that acceleration makes the age on a flat universe almost 14 billion years, coincidentally about the same as the Hubble times estimate. That age is clearly older than the oldest known star cluster, which solves the age problem. However, for many years, cosmologists have enjoyed saying, geometry is destiny. Thinking of models of open, closed, and flat universes, they concluded that the density of a model universe determines its geometry, and its geometry determines its fate. By this, they mean that if the universe is open, it must therefore expand forever. Whereas if it is closed, it must eventually begin contracting. But that is true only if the behavior of the universe is ruled completely by gravity. If dark energy causes of acceleration that can dominate gravity, then geometry is not destiny. And depending on the precise properties of the dark energy, even a closed universe must expand forever. The ultimate fate of the universe depends on the nature of dark energy. If dark energy is described by the cosmological constant, then the force driving acceleration does not change with time, and our flat universe will expand forever, with the galaxies getting farther and farther apart and using up their gas and dust, making stars. And stars dying until each galaxy is isolated, burned out, dark, and alone. If, however, dark energy is described by quintessence, then the force may be increasing with time, and the universe would accelerate faster and faster as space falls, and the galaxies away from each other, eventually pulling the galaxies apart, and then pulling the stars apart, and finally ripping individual atoms apart too. This possibility has been called the Big Rip. Probably there will be no Big Rip. Critically important observations made by the Chandra X-ray Observatory have been used to measure the amount of hot gas and dark matter in almost 30 galaxies clusters. Because the distance of each cluster is one of the variables in the calculation, the X-ray astronomers could compare the amount of hot gas and dark matter and solve for distance. The father of the cluster is 8 billion light years away. These observations are important for two reasons. First, the redshift and distance of these galaxies independently confirm the conclusion from the supernova observation that the expansion of the universe first decelerated, but changed to accelerating about 6 billion years ago. And second, the Chandra result almost completely rule out this quintessence. If dark energy is described by the cosmological constant and not by this quintessence, then there will be no Big Rip, as you can see from this graphical representation. On the largest scale, the universe is isotropic. That is, it looks the same in all directions. But on smaller scales, there are irregularities. The sky is filled with galaxies and clusters of galaxies that seem to be related to their neighbors in even larger aggregations that astronomers call large-scale structure. Studies of large-scale structure led to insights about how the universe has evolved. When you look at galaxies in the sky, you see them in clusters ranging from a few galaxies to thousands. And those clusters appear to be grouped into superclusters. The local supercluster in which we live is a roughly disc-shaped swarm of galaxy clusters, around 50 to 75 megaparsec in diameter. By measuring the redshift and positions of over 100,000 galaxies in great slices across the sky, astronomers have been able to create maps revealing that superclusters are not scattered at random. They are distributed in long, narrow filaments and thin walls that outline great voids nearly empty of galaxies. This large-scale structure is a problem because the cosmic microwave background radiation is very uniform, and that means the gas of the Big Bang must have been extremely uniform at the time of recombination. Yet, the look-back time to the fastest galaxies and quasars is about 93% of the way back to the Big Bang. How did the uniform gas at the time of the recombination coagulate so quickly to form galaxies? How did it make clusters of galaxies and the supermassive black hole we observe as the quasar so early in the history of the universe? Baryonic matter is so rare in the universe that cosmologists can calculate that it did not have enough gravity to pull itself together quickly after the Big Bang. As you have read and listened to me earlier, cosmologists propose that dark matter is non-baryonic and therefore immune to the intense radiation that prevented normal matter from contracting. Dark matter, in contrast, was able to collapse into clouds and then pull in the normal matter to begin the formation of galaxies, clusters, and superclusters. Mathematical models have been made to describe this process, and cold dark matter does seem capable of jump-starting the formation of structure of the right sizes and in the right amount of time. But what started the clumping of the dark matter? Theories say that space is filled with tiny, random quantum mechanical fluctuations, smaller than the smallest atomic particle. At the moment of inflation, those tiny fluctuations would have been stretched to very large but very subtle variations in gravitational field that could have stimulated the formation of a clusters, filaments, and the structure you see in this figure may be present-day ghostly traces of microscopic random fluctuation in the infant universe. The 2-degree field redshift wave mapped the position and redshift of 250,000 galaxies and 30,000 quasars. As expected, the galaxies are spread in filaments and balls, and a statistical analysis of the distribution matches the prediction of the inflation and shows that the current expansion is accelerating. This is an important result because it is yet another confirmation that it is independent of the brightness of type 1a supernova or X-ray emitting gas in galaxy clusters. When a theory is confirmed, the observation of many different types, scientists have much more confidence that it is a true description of nature. Let's study the curvature of the universe. Astronomers continue to search for more ways to confirm that the universe is flat and that its expansion is acceleration. One way to measure the curvature of space-time is to measure the size of the things at great look-back time. For example, observing tiny irregularities in the background radiation. That type of measurement is yielding impressive results. The background radiation is nearly isotropic. It looks almost exactly the same in all directions after effect of Earth's motion, and also emissions by material in the foreground are taken into account. After those corrections are made to map all the background radiation, and the average intensity is subtracted from each spot of the sky, small irregularities are evident. That is, some spots on the sky look a tiny bit hotter and brighter, or cooler and fainter than the average. Let's look to this figure, please. Those irregularities contains lots of information. The inflation modified Big Bang theory of the universe make specific predictions about the angular size of the variations you should find in the background radiation. Observations made by the COBE satellite COBE in 1992 detected the variation with the largest diameter, but detecting smaller variations is critical for testing the theory. 6 teams of astronomers have built specialized telescopes to make these observations. Some have flown under balloons high in the atmosphere, and others have observed from the ice of Antarctica. The most extensive observations are made by the Wilkinson Microwave Anisotropy Probe, WMAP, a space infrared telescope. You know, it is a common misconception that explosions in space produce sound. Science fiction movies imply that sound can travel through a vacuum, and that exploding spaceships make satisfying kaboom. That's not true now, of course, but the early universe was dense enough that sound could travel through the gap. And the Big Bang did make a noise. A theory describes it as a descending scream, built into a deep, rasping roar, and ending in a deafening hiss. The pitch of the sound was about 50 octaves too loud for you to hear. But those powerful sound waves did have an effect on the universe. They determined the size of the irregularities now and detectable in the cosmic microwave background radiation. Cosmologists can analyze those irregularities using sophisticated mathematics to find out how commonly the spots of different angular sizes recur. The mathematics confirm that spots about 1 degree in diameter are the most common, but spots of other sizes occur as well, and it is possible to plot a graph such as this figure to show how common different size irregularities are. Theory predicts that most of the regularities in the hot gas of the Big Bang should be about 1 degree in diameter if the universe is flat. If the universe were open, the most common irregularities would be smaller. Careful measurements of the size of the irregularities in the cosmic background radiation show that the observations fit the theory very well for a flat universe, as you can see from this figure. Not only is the only of inflation confirmed, an exciting result felt, but these data show that the universe is flat, meaning space-time has no overall curvature, which indirectly confirms the existence of dark energy and the acceleration of the universe. The data points from the WMAP observation follow a wiggling line in this figure, and the size and positions of those wiggles tell cosmologists a great deal about the universe. The details of the curve show that the universe is flat, accelerating, and will expand forever. The age of the universe derived from the data is 13.7 billion years, right? Furthermore, the smaller peaks in the curve reveal that the universe contains 4% baryonic or normal matter, 23% non-baryonic dark matter, and 73% dark matter. Dark energy. The Hubble constant is confirmed to be 71 kilometers per second per megaparsec. The inflationary theory is confirmed, and the data support the cosmological constant version of dark energy. Also, quintessence is not quite ruled out. What dark matter is ruled out. The dark matter needs to be called dark matter to clump together rapidly enough after the Big Bang to make the galaxy clusters and superclusters be observed. In fact, a model based on these data predicts that the first stars began to produce light when the universe was only about 400 million years old. Please reread the predicting lectures, okay? Especially to some people who have been working in the field for years. That collection of term facts is mind-blastingly amazing. WMAP and other studies of the cosmic microwave background radiation and the distribution of galaxies have revolutionized cosmology. At last, astronomers have accurate observations against which to test theory. The values of the basic cosmic parameters are known to a precision of 1% or so. On reviewing this result, the one cosmologist announced that cosmology is solved, but that might be premature. Cosmologists don't understand dark matter or the dark energy that drives the acceleration. So over 95% of the universe is not understood. And this is a big deal for you and another generation of people. Hearing this, another cosmologist suggested a better phrase was cosmology in crisis. Certainly, there are further mysteries to be explored, but cosmologists are growing more confident that they can describe the origin and evolution of the universe. How does inflation theory solve the flatness problem? This question requires a carefully constructed argument. The flatness problem can be stated as a question. Why is the universe so flat? After all, the density of matter in the universe would be anything from 0 to infinite. But the observed sizes of variation in the cosmic background radiation shows that the universe is namely flat. And therefore, the average density of the universe is close to the critical density. Furthermore, the density must have been astonishingly close to the critical density when the universe was very young, or it would not be so close now. The inflation theory solved this problem by proposing that the universe had a moment of rapid inflation when it was a tiny fraction of a second old. That inflation drove the universe toward flatness, just as blowing up a balloon makes a spot on the balloon flatter and flatter. Understanding theory in cosmology is critically important, but science depends on evidence. Now build another argument based on evidence. What evidence can you cite that the expansion of the universe is accelerating? And now let's get some summary. Cosmology is the study of the structure and history of the universe as a whole. Astronomers and physicists who do research in cosmology are called cosmologists. Cosmologists include that it is impossible for the universe to have an edge because the edge would introduce logical inconsistency. In other words, an edge to the universe does not make sense. If the universe has no edge, then it cannot have a center, right? The darkness of the night sky leads to the conclusion that the universe is not infinitely old. If the universe were infinite in extent, infinite in age and static, then even spot on the sky would glow as brightly as the surface of a star. This problem, commonly labeled Olber's paradox, implies that the universe had a beginning. The observable universe, the part you can see from Earth with a large telescope, is limited in size. It is possibly only a tiny portion of the entire universe which could be infinite. Edwin Hubble, 1929, discovered that the redshift of a galaxy is proportional to its distance, known as the Hubble law, shows that the galaxies are moving away from each other. That phenomenon is called the expanding universe. Tracing the expansion of the universe backward in time brings you to the imagined and initial high density, high temperature state commonly called the Big Bang. A rough estimate of the age of the universe based on the presently observed expansion rate is called the Hubble time. Also, the expanding universe began from the Big Bang. It has no center. The galaxies do not move away from a single point. Cosmologists understand that galaxies remain approximately in their respective position and become farther away from each other as the space between them expands. The cosmic microwave background radiation is black body radiation with a temperature of about 2.73 Kelvin and spread nearly uniformly over the entire sky. This radiation is the light from the Big Bang, freed from the gas at the time of recombination, and now redshifted by a factor of 1,100. The background radiation is clearly evidence that the universe began with a Big Bang. During the earliest moments of the universe, matter and antimatter particles continually flashed in and out of existence. A slight excess of ordinary matter remained after the most of the matter and antimatter particles annihilated each other. During the first 3 minutes of the Big Bang, nuclear fusion converted some of the hydrogen into helium, but was unable to make many other heavy atoms because no stable nucleus exists with weights of 5 and 8. Now, hydrogen and helium are common in the universe, but heavier atoms are rare. After recombination, for a period of hundreds of millions of years, called the Dark Age, the universe expanded in the darkness until the first stars came into existence. Astronomers have observed signs of reionization of the universe caused by the first generation of stars. The chemical composition of the oldest stars is about 75% hydrogen and 25% helium, which is what models of the Big Bang nuclear processes predict. This is further evidence supporting the Big Bang theory. The universe is isotropic and homogeneous. In other words, in its major features, the universe looks the same in all directions and in all locations. Isotropy and homogeneity lead to the cosmological principle, the idea that there are no special places in the universe, except for minor local differences. Every place is the same, and the view from every place is the same. Einstein's theory of general relativity explains that cosmic redshifts are caused by wavelengths of photons stretching as they travel through expanding space-time. Closed universe models are finite in size, but their space-time is carved back on itself, so they have no edge or center. Open universe models have covered space-time, but it is not carved back on itself. Such universes are infinite. Flat universe models have uncarved space-time and are infinite. Modern observations show that the universe is probably flat. Open model universes contain less than the critical density, and closed model universes more. If the universe is flat, then its density must equal the critical density. The amounts of deuterium and lithium-7 in the universe shows that the normal baryonic matter can make up only 4% of the critical density. Dark matter must be non-baryonic and appears to make up less than 30% of the critical density. One hypothesis for what dark matter might be is a type of subatomic particles labeled WIMP. The observed ranges of the sizes and masses for galaxy clusters disagrees with models that assume rapidly moving hot dark matter particles that would not clump together easily enough, and agrees with models that assume slowly moving cold dark matter. Inflationary in universe, a modification to the Big Bang theory, proposes that the universe briefly expanded dramatically, just a tiny fraction of a second after the Big Bang. The energy to drive inflation would have been released when the four sources of nature changed their respective properties, as the universe called it in its earliest form. This separation of forces is predicted by Grand Unified Theory, JUT, that explains the forces of nature as being aspects of single force, and unified in particle interaction with very high energy. Inflation explains the flatness problem because the large expansion forces the universe to become flat, as a spot on an inflating balloon becomes flatter as the balloon inflates. Inflation explains the horizon problem because what is now the observable part of the universe was so small before inflation that energy could move and equalize the temperature everywhere in the body. Observations of type 1a supernova reveal the surprising fact that the expansion of the universe is speeding up. Cosmologists propose that this acceleration is caused by energy present in empty space, labeled dark energy. The nature of dark energy is unknown. It may be described by Einstein's cosmological constant lambda, inverse lambda, okay? Or its strength may change with time, which cosmologists label quintessence. Some models of quintessence predict an ever accelerating expansion leading to a big rip, that eventually would tear all the objects, even the atom of the universe apart. Corrected for acceleration, the observed value of the Hubble constant implies that the universe is 13.7 billion years old. The sudden inflation of the universe is thought to have magnified tiny quantum mechanical fluctuations in the density of matter and energy. These very wide but very big differences in density cause dark matter, followed by baryonic matter, to draw together and produce the present-day large-scale structure consisting of galaxy superclusters arranged in great walls and filaments outlining enormous forms. Statistical observation of the large-scale structure of the universe confirm that it is flat and contains 2% baryonic matter, 23% dark matter, and 73% dark energy. The mass equivalent of dark energy added to dark matter and baryonic matter makes the observed density of the universe equal to the critical density, thereby confirming the prediction made by inflation theory that the universe is flat. I think it's enough for today. Next time we will have our final lecture. Okay? For this moment, any questions or propositions? It must be, if you listen me carefully, because it's really, really very interesting and very, very difficult topic of science. Nevertheless, I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.